My talk is about reconciling cosmic dipolar tensions with a GPC scale void, which is based on the two papers. In the cosmological standard model, is based on a very important principle, that is a cosmological principle. Our universe is homogeneous and isotropic on that scale, independent of location. The cosmological principle indicates a very important result, that is, the law of physics should be the same at different positions of the universe. The cosmological principle has already been proved in a lot of observations, for example, the cosmic microwave background and the large-scale structure. However, we still observed some inhomogeneity in observations, such as we have already find a lot of void structure in the large-scale structure. Especially, there is a void structure called KBC void with a radius of 300 microsecond, especially because our Milky Way lives inside it. Also, we observed some cosmic anisotropy. For example, the CMB temperature dipole in the galaxy coordinate system. In detected Quantum number density distribution, we also find a Quantum number dipole with the amplitude around 10 to minus 2 in the similar direction of the CMB temperature dipole. In order to explain such a cosmic anisotropy in the framework of the lambda CDM model, we want to use the Doppler motion of our solar system in the frame of the CMB to explain it. And the Doppler effect in CMB temperature, we can find the amplitude of dipole is proportional to the peculiar velocity of the solar system, which is around 369 kilometers per second. Also, we can use this Doppler motion of the solar system to explain the observed Quantum number counting dipole. And we can find that the amplitude of the dipole is all still proportional to the velocity of our solar system, and it gives a velocity around 700 kilometers per second. Then we can find the to obtain the peculiar velocity are different. There are 4.9 sigma difference between the CMB dipole and the Quantum number dipole. And the difference in their direction is within 1 sigma, so it's fine. Therefore, we call such 4.9 sigma inconsistency in their dipole amplitude as the dipolar tension. This dipolar tension indicates that in our universe there exists some anisotropic structure. For example, the global anisotropic structure. That is, maybe our universe is not FRW in universe, maybe it's BNH universe. However, this work shows that the BNH cosmology has been strongly constrained by the CMB observation. Another possibility is maybe our universe is rotating. There is a special axis. And in this work, they show that the angular velocity of the universe is strongly constrained. Therefore, a local structure may exist, and such a local structure may influence our observation. So this local structure means a local void. Local void means the inside this range, the matter density is smaller than the matter density outside. And such a local void will cause some observation, such as if the nearby type 1a supernova also live inside this local void, they will be attracted to the outside range, a high matter density range. Therefore, in our observation, we will obtain a higher measured Hubble parameter, which causes the Hubble tension. And because we want to include all the detected type 1a supernova inside the void, therefore this void should be a GPC scale. Another is if our Milky Way lives inside the void, it is highly possible that our Milky Way is not at the center of the void. Our Milky Way is at an off-center position. And such an offset position will cause the matter density distribution in our observation is anisotropic. Such an anisotropic matter density distribution will cause an anisotropic spacetime, and this anisotropic spacetime will induce a dipole structure in our observation. However, such a GPC scale local void can hardly be produced in the standard cosmology. Therefore, we need some probability mechanism. Here we use the multi-stream inflation as a mechanism to produce such a GPC scale local void. During the inflation, when inflaton encounter a barrier, the inflation trajectory will bifurcate into two trajectories. The different trajectories has a different enfolding number, and for the inflaton travel on this short enfolding number trajectory, the inflation ends earlier, and the range will start the expansion earlier and cause the matter density dilute. This will induce such a local void. And the size of this void is controlled by this bifurcation scale, and the depth of the void is controlled by the enfolding number density between these two trajectories. Then the thickness of this void is controlled by the difference of the bifurcation scale and the combination scale. Here we use three parameters to parameterize the void profile as this one, the void depth, void radius, and void thickness, which is related with the inflation parameter. So let's first take a look at Hubble tension in this GPC scale local void, which is based on this paper. In order to describe the void model, we use the Normie-Tolman bounding metric, which is used to describe the inhomogeneous but isotropic spacetime. Then we can solve the Friedmann equation. Then we find that the Hubble parameter inside the local void is larger than the Hubble parameter outside the void, and the Hubble parameter difference is controlled by the void depth. If you want to explain the Hubble tension, solve the Hubble tension, the void depth should be the minus 0.4, which means the matter density contrast between the inside void and outside void is 40%. However, such a deep void is strongly constrained by observation, such as the BL observation. We use this BL observable to constrain the void profile. We can find that if void is deeper, is strongly constrained by BL. Another one is the canonical Suryava-Zadovich effect in the CMB, which will constrain the void profile, because when the electron inside the void will has a peculiar velocity outside towards the outside void, and this peculiar velocity intact with CMB photon will cause a temperature distortion. We will find it will constrain. It can constrain the void profile, and we find that for 1.7 GPC void, the deepest all-load void is around minus 0.14. And this kind of void depth can only is Hubble tension from 5 sigma to 3.5 sigma. Therefore, such a GPC scale local void can only ease the Hubble tension, but cannot solve the Hubble tension. Another one is the cosmic dipole in this GPC scale local void, which is based on this paper. Just as we introduced that our position inside local void should be the offcenter. This offcenter position will induce an anisotropic space-time, which cause the dipole structure in observable. Here, in order to solve this anisotropic space-time, we first use LTB metric and solve the geodesic equations of the CMB photon, and you find their redshift distribution. Then we can find that we can calculate the dipole amplitude in the observed CMB temperature anisotropic. We find that if the distance between the center of the void and us is larger, the amplitude will be larger. And if we consider this void profile and combine with the observed CMB dipole amplitude, this means the distance between the void center and us is 492 megasecond. Also, we can calculate this redshift dipole caused by the anisotropic space-time from a low redshift to a high redshift. Then we can find there is a peak dipole amplitude occur on the boundary of the void. And if such a void boundary or such a peak appears around the redshift of the quasar, this amplitude peak can explain the dipole tension between the quasar dipole and the CMB dipole. Therefore, we need to calculate how the quasar dipole behavior in this anisotropic spacetime. Therefore, we first need to know how the anisotropic spacetime causes the dipole in quasar dipole. The photon from the quasars will be shifted by the anisotropic spacetime, by this anisotropic redshift, and this will cause a dipole structure in observed quasar's photon, and this this dipole in quasar's photon frequency will cause a dipole in observed flux distribution of the quasars, and this flux distribution is related with the quasar's number counting. Therefore, we can find a dipole structure in quasar number counting, which is related with redshift dipole in this anisotropic spacetime. Also, we can also assume the quasar number density is proportional to the matter density in this local void. Therefore, the dipole of the quasar number should be the same order of the matter density dipole. And for the matter density dipole, we can first principally calculate it in our local void scenario by this equation. Then we find that for void profile, we choose at the high redshift, it can naturally explain the CMB dipole, and around the boundary of the void, the peak behavior of this anisotropic spacetime can explain the observed quasar dipole and decrease the dipole tension between the quasar dipole and the CMB dipole from 4.9 sigma to 1 sigma. And also, in the future observation, if we can observe the 21 centimeter background, the gravitational wave background, they also have some dipole structure. And if really there is a local void structure, the dipole structure in 21 centimeter structure and the background and the gravitational wave background should be similar. And for the supernova observation and large-scale structure, because their redshift is relatively small, therefore the induced anisotropic structure in this kind of observation is very small, so it's hard to be detected. Then it means the cosmic dipole in the global signals can indicate the profile of a local structure. This result is very important. So in this scenario, our universe is homogeneous and isotropic, but with a local void embedded, and our Milky Way lives inside this local void. This will cause the observed hypotension and observed dipolar tension. Thank you.